Hi, Recon. Good afternoon. Everybody's awake. Come on. Noise, noise. Thanks. It is a pleasure to be here. It is 10 years that I joined this community. For me, it's a great honor to be there, stand in front of you, because seated there are ex-students of us. There is our first trainer we took here. There are friends that we meet every year, and it is nice to see how the reverse community grow, do stuff, and react to the change of the world. So, thanks to show up, interesting to our research, we will talk about adversary emulation, false flag, Chinese APTs, obfuscation. What do you want more? Okay, so let's introduce us. We are the Italians that come every year there. My name is Silvio. There is Antonio. We have Giulio. We create our own company, and what we do daily is reversing malware and rewrite that malware in our adversary emulation platform. That is how we spend the days. And for the rest, we go around doing training, and what we teach, developing malware. Come on. One topic, nothing more. I don't know anything about food and cooking because I'm Italian. For the rest, don't ask me about physics, math. There is Sergey there that know everything, and the compilers. So, previous to create my own company, I worked as a reverser last 20 years almost. I am not yet tired to reverse malware. So, but my hair starts to be too much gray. And yeah, I started doing a PhD. So I was young, and even that make trouble. Giulio participated to that research doing his own master degree thesis. So it is part of Giulio work that disappeared, but I hope that at some point they will show up again. Okay, so let's introduce the red team offensive part that is start to be real common in Recon. So there is an evolution on the offensive part. So we started 12 years ago talking about vulnerability assessment, penetration testing, and after a while it appears the red team. So why red team matters? First of all, test the defense. This is the first point. Second point, identify gaps on the detection points of the organization. It's fun because we evade EDR, AV, 1,000 million of software, whatever. And last but not least, enhance the blue team detection capability. So the first time of the red team should be training the blue team on detect and react to a specific threat actor. That is the first time. But sometimes it's not. So what are the types of engagement that today you can get? So you have the adversary simulation. It is the pretty old one, where basically you mimic tactics, technique, procedure of generic threat actor. Sorry. And typically you use commercial tools or stuff that you find on Git. I use the term stuff. And the goal is to evaluate and the response to security control. So evaluate the detection capability of an organization. After last years started to, everybody is saying, we are doing adversary emulation. We are doing adversary emulation. So what does it mean? So instead of having a generic, you go to a specific threats, specific implants. That requires development, because you need to understand the tradecraft and re-implement that. And the goal is not to testing against a generic, but against something specific for the blue team. Okay. What is the reality? People is not developing tradecraft, specific tradecraft, but is developing random stuff that are able to evade detection. That is something that is outside the goal of the adversary emulation. So let me do a concrete example, right? So if you use the Mitre attack catalog plus the malware behavior catalog, combining these two frameworks, that is much a huge effort to classify implants behavior, you should be able to provide a good adversary emulation activity, right? Implementation. But starting directly from the source of the information, if we, for example, get a PT3 and plug X, that is the most famous implant that the Chinese crew used, if we go to look this capability, and I want just that we focus on one specific, not everything, but one specific, on the discovery part, the discovery process capability. The discovery process capability is identified by the MITRE as the T1015, and if you read the description, is the capability that an implant has to list the process that are running in a machine. Nothing is so complex, right? In the description itself, it is named just one API, that is create tool help 32 snapshot. But if I show you this, and everybody in this room should understand that, what is that? It's a piece of code. Thanks, guys. So, tell me more. So it is the piece of code of plug X to implement the discovery, process discovery capability. And for that specific implants, it uses enumerate process and open process token that is completely different. Okay, let me show you something. What is that? Other piece of code. Good. So, same stuff again. It is exactly. It is the other implementation of the same capability, process discovery, using other different APIs. The one on the left is Latrodectus, and the Lumma is on the right. Lumma Stealer. Okay. So only focusing on just point, MITRE said that there is 195 implants that use that capability, and potentially with 195 implementation. Yeah, sure, some implementation will be co-lead, some will use the same API, but potentially there are different way of implementation. But when you do some emulation, what you see is just T1057. It's not one specific. And the detect is completely different than the detect the other one, and so on. Because it is a different artifact that left on the log, differ absolutely from detection point of view, two different completely words. And we are just talking about something really small comparing the entire ecosystem. So we need something different. So we introduce the term false flag emulation because the term adversary emulation is abused. So what is the false flag? It is the emulation that is able to imitate tactics, technique, and procedure of a specific threat actor implant, as so close as much that is identical to the original, or even better than the original in some case, because people fix. So, and that requires to develop. What do you need to develop? You need to develop all the functionality implemented in the implant. You need to develop the communication protocol, and even the obfuscation if an implant does it. Because even when you obfuscate an implant, it became, even from the detection point of view, something completely different from detect, from the unobfuscated one. Okay. So let me make a sum of these 5 minutes. And what we have from adversary simulation, the complexity is really low. The time required is really small. But what you obtain is relevant or not? Is something. Come on, let's say it's something. So for adversary emulation instead, the complexity became medium to high. The time required, if you implement, became longer. And it requires more skills. So you need the red team operator, a malware dev, and a CTI analyst that at least say something about what you are doing. And the you get, it wanna be realistic, that is the aim, and you need, what today you have is a custom tradecraft implementation. With the false flag, stuff change. So the game is changing because you need another skill that is the reverser guy that is able to go deep in the implant and shape the implementation. The time required is really long. But what you obtain is something different. Is really you can test the robustness of your detection system, procedure, SOC, human, whatever you want. So let me make it visual. Italian food, yeah? So you have adversary emulation and a false flag. Something completely different. It's always someone that is doing something, but in the different way. So let me show you the approach that we use during the implementation. So first, we target a specific implants, and we start to analyze it. So get source of incident, get the implant, start to reverse it, use a bunch of tools to extract behavior, feature, open on IDA, try to remake exactly the same shape of the binary, means section, and if there is an obfuscator, give a look to the obfuscator and try to implement that. Reimplement everything, a bunch of time, a bunch of effort, and after you need to test. Even with our try, even if we try to be so close, there is always a slightly modification. And in some cases, that slightly modification is enough to evade a detection. And if we try to tweak and slightly change the what we implemented, that give another result, a different result. Okay, so that is the theory part. You know what, where I am going to lead you. Chinese, okay. So for make that concrete what I'm saying, we will show the work that we did on APT41. APT41 is a Chinese threat actor that is engaged in cyber espionage, attacking a supply chain, do a bunch of activity, and it's developed its own obfuscator for its implant. So, Giulio is here, and the floor is you.
Thank you. Thank you. Is this on? Yeah, okay. Allora, so this talk, we start with a brief introduction on APT41 and their obfuscating compiler, along with the employed techniques. And I'll talk about how we tried to replicate them, the choice we have made in that sense, and limitations we encountered, and how we eventually validated our work. So lastly, I'll talk about how we broke some of the deobfuscator heuristics. And the following information about Scatterbrain's internal workings is based on the thorough Mandiant article, on which part of our work is also based, as well as the PWC one. And along with the blog post, Mandiant also open sourced the fully functional deobfuscator. So by far, Scatterbrain's most interesting technique is the instruction dispatcher. This simple yet extremely effective obfuscation method radically changes a program's control flow by scattering the basic blocks throughout the binary. Each basic block consists of a legitimate instruction doing some work, and then a call to a block-specific dispatch function. And immediately afterwards lies an encoded 32-bit value called the displacement. So each dispatcher routine follows a carefully crafted sequence of instruction, you can see. And it first retrieves the displacement following the call, then proceeds to decode it via one of the available methods. And finally, it adds or subtracts the result from the value saved on a stack, and from the return value saved on a stack. And when the dispatcher returns, it won't be to the previously saved return address, but rather to the newly computed destination address, which is also the address of the next legitimate instruction. And it also preserves the working register along with the register flag values, which may be changed to do the decoding operation. by pushing and popping them onto an of the stack. In addition to that, each dispatcher instruction is followed by a pair if jump if condition is met, also known as JCC, and targeting the same destination address, but with opposite condition. And this effectively creates an unconditional jump because no matter what the register flag values are, one branch is always taken and led to the very same destination address. The second protection layer is a fairly common one in this type of malware, and it obscures the system API usages by dynamically resolving them at runtime through the usage of load library and get procedure address in a dedicated resolver routine. For each import, a unique structure holding the necessary information to perform its decryption is created. And such informations are the relative virtual address of the variable storing the DLL name, the encrypted DLL name, the RVA of the variable storing the encrypted API name, and also a pointer where to store the API address once it's been resolved. And the original call instruction is then replaced with a call to a dedicated stub routine containing an hard-coded reference to an obfuscated import structure. So the encryption scheme works as follows. The first 4 bytes of a randomly generated number are used as a seed for the linear congruential generator, and the LCG state is computed as shown here, where A is 17 and C is a sample-specific constant. And the current state, first 4 bytes, are then extracted to get the XORing key, which will then be used to encrypt the actual string character. And when the string terminator is reached, the LCG state is appended to signal the string termination during the decryption phase. So now let's talk about how what we chose to use in order to replicate said techniques. And despite obviously not knowing what APT41 used, we chose the LLVM infrastructure for our implementation due to its robustness, its maturity, and because we were already familiar with. And it featured an extensive IR representation where common to the all sorts languages it supports, where it operates optimization before translating the IR code to the target native code. So our pipeline first converts the given source code to its IR4 through CLang, then loads a previously compiled shared object containing the obfuscation pass and applies the predefined set of rules to the input IR, and finally cross-compiles the obfuscated form to a PE x86 native code. And our approach is the so-called out-of-source compilation, because the IR passes can be loaded dynamically against an existing installation without the need to recompile the entire LLVM infrastructure. And in LLVM, passes are simply the way optimization is done. So each optimization is implemented through one of them. And let's have a look at how we emulated the instruction dispatcher technique. So given any source code in input, in order to replicate what we have seen with the instruction dispatcher, we have identified 3 necessary steps to perform, to be taken. We need to move each instruction to its own dedicated block. Then we need to create a unique dispatcher and emit a call to it. And finally, we need to somehow emit the encoded displacement. Oh, scusa. Sorry. So it's first necessary to relocate each instruction to its own dedicated block. Ideally, by doing so, we should be able to have a single dispatcher protecting a single instruction, although we will see later why this is not the case. Anyway, to accomplish this, we leverage the split basic block method to split existing basic blocks in half at each instruction. And the process is repeated until the block terminator is reached. And the great thing is that this method handles all the underlying details about moving blocks, branching them accordingly, updating operands, etc. And now the dispatcher function itself. So the next step involves creating unique dispatcher function and integrating into them the opposing conditional jumps. So in order to replicate the exact instruction sequence, we make use of the LLVM inline ASM feature that allows us to embed assembly code directly in the IR. And this way we can maintain precise control over the generated instruction. This wouldn't be possible if we chose to work only with the IR. And a random register from one of those available and a 32-bit encoding key are generated via two simple helper functions that we wrote. The strings are actually used to randomize the dispatcher instructions. And in order to alternate each instruction with a pair of opposing conditional jump, we store them as a string and a vector of string. And this way, after each dispatcher instruction has been emitted, we can also emit a pair of GCC by first selecting its type and it's negated. And via a simple helper function, again, that we wrote. The $0p syntax is the LLVM inline assembly parameter substitution that allows the destination target to be passed as an argument to the inline ASM call. But how do we provide valid destination address to both jumps? In LLVM IR, there is no concept of concrete address because it's an intermediate representation designed to be target independent, and address allocation and layout are not handled until much later when the IR is translated to native target code and the linker has done its job. So later on, this proved to be a limitation of the chosen IR-based approach. Luckily, LLVM block address let us reference basic block addresses during the IR manipulation phase without actually knowing them yet. And the same block address is fed as argument to the opposing conditional jump. And the linker would then substitute them both with the real address during the linking phase. In addition to that, each IR basic block needs a proper block terminator from one of the available. So either a branch instruction, an invoke instruction, return, or even an unreachable one. Despite the dispatcher basic block ending with a conditional jump, LLVM doesn't recognize them as a proper block terminator because it's inline ASM. So among the possibilities we chose to add an indirect branch instruction that actually solves a problem that will arise later on. And in fact, the compiler is smart enough to recognize that previously split relocated instructions have no real reason to be separated and proceeds to merge them. The indirect branch instruction prevents this. So this is what a dispatch basic block looks like at the intermediate level. You can see it begins with an inline ASM call to one of the dispatcher sequences instruction, in this case push R15. Then there's the opposing conditional jumps, in this case interleaved with a dummy move, a no operation move. And finally, the indirect branch acting as a proper block terminator. And additionally, in order to prevent compiler from applying optimization, forcing inlining, or even creating prologues or epilogues, we mark the function with three attributes: the naked, the no inline, and the optimized none. And now let's see how we can compute the displacement. See, this is probably the most interesting challenge and the hardest one we faced during the emulation, the displacement calculation. So there are two conditions that need to be met in order to create the displacement. We need to be able to compute the distance in terms of bytes from one IR instruction to the subsequent, to the next. Because if you recall, the displacement is simply the difference between the next legitimate instruction and the return address of the dispatch function call. So this may be viable by converting both addresses to integer and perform any operation needed on them. But we didn't investigate this any further because of the following requirement. So the second condition proved to be the real showstopper. So in addition to being able to compute the distance, we also need to be able to emit it in terms of raw bytes. And in traditional assembly, you can emit using directives such as the .byte for 8-bit, .word, .long, and .quad. But these directives are static, meaning that they require compile time constants and do not accept block address, unlike the jumps. So the first approach we took was to compute them afterwards, post-compilation, by first inserting a reliable and repeated placeholder, which will then be later identified and overwritten. And in order to have both a valid terminator and prevent branch folding, we again chose to replace each unconditional direct jump with an unconditional indirect one. And the translation from IR instruction to the native code gives us a reliable instruction sequence of 9 bytes, the 7 for the load effective address plus 2 for the jump, which is more than enough. Also, as seen in the available APT41 samples, both dispatcher and obfuscated function basic blocks are shuffled within the function. This is easily replicable in LLVM thanks to the single static assignment IR form that ensures that basic blocks relative order doesn't affect the program correctness because each variable is assigned exactly once and never reassigned, so references are unambiguous. And as you can see in the image, the shuffled basic block order in the IR form is reflected into the final binary, provided we disable optimization, of course, and the program runs anyway. In the picture, you can see the current state we're at. So after applying obfuscation to an example input IR and compiling it to native code, each basic block has one, or as you can probably already tell, multiple legitimate instruction, a call to a block-specific dispatch function, and it ends with the load effective address plus jump instruction pair. And you can probably can't probably tell, but the basic blocks are shuffled. And let's see what we have to do in the post-compilation. So once compiled into the P format, we use the Python spfile library and the capstone disassembler to identify and classify function, dynamically extract the dispatch function encoding keys, detect the inserted placeholder, and compute the displacement. And finally, clean up any leftover. So both the obfuscated function and the dispatch function have been previously marked with the DLL export class to ease their identification and retrieval in the post-processing phase. This way, we can gather them by simply parsing the p export directory. And the distinction between the two is made using the naming convention that the dispatch function follows. And we then disassemble each dispatcher function to extract the encoding key we'll use for the displacement encoding. And this approach is crucial because each dispatch function features a randomly generated encoding key. Then the core processing loop scans each target, looking for our reliable placeholder pattern, which is a call to a dispatch function, followed by the load effective address plus jump pair, instruction pair, and it computes the distance between the call site and the next legitimate instruction, encodes with the previously instructed encoding key, and finally overwrites the placeholder with the 4 bytes displacement, encoded displacement, plus 5 random bytes. We also take the opportunity to clean up any traces that could undermine our obfuscation. Firstly, we erase the export directory, and secondly, we overwrite the indirect jump that acted as a proper block terminator for the dispatch function blocks. So here on the left, you can see the test case binary, how the test case binary look like, how it looks after the obfuscation pass has been applied to its input IR. And finally, you can see after the placeholder have been overwritten by displacement, how the disassembler fails to make sense of most of the function. But what if I told you there is a way to compute displacements without needing any post-compilation work at all? Yeah. The second approach we investigated came from the fact that inline assembly directives do actually take something as an argument, local labels. As per documentation, a local label is just like an ordinary label, except it can only be referenced within the function in which it's declared. But what does this mean for us? Let me show you a clarifying example. If you look to the left of the picture, you see some C code that uses inline ASP to call a long directive, taking a local label as an argument. The local label is defined right before the return instruction. And if you look to the object dump code, you can see the address of the return instruction, whose opcode is C3, being emitted obviously encoded in literal endian before it. The address is misinterpreted as opcode, which is exactly why this obfuscation is so powerful. In addition to a single label, directives also accept operations on them, such as sum or subtraction. So you can probably see where this is going, right? What's shown here will yield exactly the distance in terms of bytes between 2 instructions that we needed. And the great thing is that we'll let the linker compute it for us. So we don't need any post-compilation work at all. And the new plan is simple. We need to insert a label at the beginning of each block. Let's call it the starting label. And then we need to insert a label after the dispatch call, the ending label. And we need to insert a long directive computing the difference between the next basic block starting label and the current basic block ending label. And we use inline ASM to emit all of the above. Yeah, so a few details about it. The ending block label must come right after the displacement, and therefore the inline ASP call can be merged together. Another interesting fact is that we also need to account for the long instruction size, which is 4 bytes, to get the actual return address. And finally, we can encode it all with the XOR operation, with an encoding operation, by simply appending the operation. So you can see the output in terms of intermediate representation of the steps I just described. The ending label of the current basic block is being subtracted to the starting label of the next basic block, which represents the next legitimate instruction. We also account for the long instruction size, and then we encode it all with the encoding key, the current encoding key. So you may be wondering what the letter F stands for. It actually means that it's a forward reference, And on the other end, B stands for a backward reference. This posed a problem whenever the blocks were shuffled, because we needed to know whether the reference was to a subsequent block, or so a forward reference, or to a preceding one. And this is solved by simply tracking each basic block position inside the function and computing the distance between the successor via std distance, and then conditionally emitting F or B. Yep. As you probably have already seen, the limitation of both approaches is that the number of legitimate instructions per basic block isn't always one, like we expected it to be after the relocation step, but multiple. This happens because the translation from IR to machine code is not always one-to-one. So we actually need something closer to the machine instruction than the intermediate representation. Luckily, LLVM allows the creation of machine function passes that operate on the instruction right before they are inserted into the final binary. And unfortunately, we cannot load them dynamically as we did with the IR passes, and we are forced to recompile the LLVM infrastructure, actually a small part of it, each time a change is made. So I'll spare you the details, but the general idea is to replicate what is done with the intermediate representation with the second approach, only this time using the machine function pass APIs. So this approach proved to be the most adherent one to the original samples, and yet the least flexible one. And one constraint we found is that new function cannot be emitted at this stage. So dispatch function must be already present, perhaps emitted during the IR manipulation phase. And we actually didn't progress any further in this sense because we spent far too much time on the instruction dispatch. So now I'll take a look at how the import protection has been implemented. And in order to make the binary run successfully, the decryption routine must be present in each and every obfuscated binary. So for simplicity, we choose to LLVM link a separate bitcode containing both the import decryption string routine and the resolver routine to each input bitcode. And the steps that we need to take in order to replace the original API imports are: we need to gather the external module imports. For each one of them, we need to create obfuscated import structure and initialize its members. We need to emit a dedicated stub. And finally, we can replace the original call usages with the stub. So finding imported function is as simple as iterating over modules function and looking for the one tagged as DLL import storage class. A module in LLVM simply represents a source file or a translation unit. Unfortunately, LLVM does not provide information about which DLL exports the function. So we added a step where we precompile the source code, parse its import directory, and save the imported function externally. Next, we need to encrypt both the DLL and API names via the encryption routine I previously described. And we then create a global variable for both of them, and we initialize them with the respective encoded strings. A global variable, as names suggest, is just a variable with global scope. And once we have done that, we can create the obfuscated import structure and store the relative virtual address of both the global variable, all the encrypted names. To do that, we use the getPointer to int function that converts the global address global variable address to an integer. So you can see an example of what I just described. The original API import has been removed, and two more global variables representing the encrypted DLL name and encrypted API name have been created. And the obfuscated import structure has been created, also referencing both of the global variable addresses. The stub is then emitted using the inline ASM feature to replicate, again, exactly the original structure. The stub is parametric with respect to the loaded obfuscated import structure and the resolver routine code. So as you can see, register used by the resolver routine are saved before the call and restored after, ensuring that arguments are properly passed from the stub to the actual API. So what's left is only to replace every original API call instruction referencing the Windows import with the stub by iterating over the function uses and replacing the called operand of the call instruction with the stub. Validate our work with the deobfuscator, open source by Mandiant, using some moderately sized test cases. And as the output shows, the tool is able to find numerous dispatcher function and subsequently recovering them. And protected imports are also successfully recovered, shown here. And the obfuscated binary is then rebuilt. An interesting consideration we can make is that, as it's often the case with obfuscation, the execution time and the binary size are increased by more than a factor of 20 and 30, respectively. This degradation is easily explained by the fact that for each original instruction, from 18 to 30 new ones are added and executed. And also we can reasonably expect caching mechanism to fail because of displacement and because of the indirect redirection of the control flow happening via the dispatcher. So it is an example of how from one single instruction we go to, we now have to execute 9 dispatcher instructions plus 3 more for each dispatcher instruction, which are the opposing conditional jumps. Plus there's the call to the dispatch function itself. Yeah. So this video showcases the similarities of our obfuscated binary with the APT41 available sample. This is the APT41 sample. As you can see, there are the opposing conditional jumps interleaved with the dummy move, and these are obfuscated sample. And again, you can see the structure and this assembler failing to make sense of most of it. Yeah. And here instead, you'll see 3 binaries. So the first one is our obfuscated test case, again. The second is the original test case compiled, so non-obfuscated. And the last one is the deobfuscated version. Yeah. So although some instructions are different for obvious reason, the CFG of the deobfuscated and the non-obfuscated version looks very similar. yeah, the deobfuscator tool didn't always work with the bigger test cases, and we often wonder why until we actually forked it and had a look at it. So it turns out that it failed even with some of the scatterbrains samples we had. And after finding the issue and fixing it, we wrote the author to make sure that the tool kept working on his part. And he said it did. So thanks, Nino. And after all, so we're not just bad guys, you know. Speaking of bad guys, I saved some goodies for last. So we spent as much time reversing the available APT41 samples as we did studying the deobfuscator tool, mainly for better understanding how certain details were handled. So this led us to identifying some weaknesses in heuristics that could potentially be used to break it. And first of all, the dispatcher relies on a brute force search to find any E8 near call statements. And potential dispatcher are then verified by looking for the pushFQ, popFQ per instruction. Inspecting the verified dispatcher pushFQ function, we spotted another constraint. The dispatcher verification is limited to only 15 instructions. And additionally, if any call or jump or privileged instruction is found, the dispatcher is considered immediately invalid. So in order to break the heuristics, we can either find a pushFQ, popFQ alternative, we can create a longer dispatcher, or we can insert a call or a jump in it. But why choosing? And we can do all three. The SAHF, LAHF is a more limited alternative to the pushFQ, popFQ instructions that respectively store and load the low byte of the flags register to the second low byte of RAX. So theoretically, the only register left out that could potentially be overwritten by the displacement decoding operation and still being used in the jump with condition is the overflow flag. So although there is some way to save it via set OAL, there is no easy way to restore it. So this is solved by triggering manually the overflow in case the register flag values was set by moving the biggest 1 byte number into AL and incrementing it. And inserting a call or a jump in it, it's as easy as inserting a useless jump after the overflow flag recovery part to invalidate all the search. And this will also collaterally lengthen the dispatcher by more than 15 instructions. And shown here is the deobfuscator output once applied to the very same test case we showcased previously, with the updated dispatcher failing to retrieve any potential dispatcher. So thank you for your attention.
So we publish on our blog the long version of this, because this was a huge effort from Giulio to compress all the information and all the stuff. So if you want to go deep, there is a 13 page that is waiting for your attention. If you have any questions. Okay, means that it was really clear and sharp enough. Thank you again, guys.